This is elastic system. Okay. This is SAE. This is SBE. This is inelastic system. This is SBY. Okay. This is our ratio, not the difference. Ratio. And this is our SB inelastic. So ratio of R, so this R is equal to square root 2 minus. Okay. So what you are saying?
How R is equal to SBU by
SB.
by
SBU is actually SB inelastic. So SB inelastic divided by SB elastic. That's ratio you are. Okay. So this will be SB inelastic divided by SBY into SB y over SBE. Okay. So SB inelastic over SBY is how much? Mu. And SBY over SBE. SBE over SBY, that will be equal to R. So that will be equal to mu over square root 2, or SB inelastic will be equal to, this is the okay. Any other question? Discuss what? Second question, okay. So which one? We discussed both the questions yesterday. They asked us. Second question. So in second question we have given three-story building, mass was given. Okay. So first we have to obtain let us say SA versus SB or BB versus delta. This we have to obtain. So you know this period TE, you know SAY. Can you calculate SDY? Because SDY is simply SAY over omega square, so that is TE square divided by 4 square. What else? Ductility is given or ductility demand is asked? Ductility demand is asked. So you know this curve for mu equal to 1. Response spectrum for mu equal to 1. What you have to do? You have to assume a value of, let us say, the target point as B1. You know mu here. For this mu, you will plot the reduced response spectrum. Okay. Then either you convert this into SD versus T, or you can do the calculations from here itself. So the period remains TE At this you will get the value of SAY, actually this SAY, then you can calculate SAY as SA into SAY into T square divided by 4 pi square. Then you can calculate SB inelastic or SB, that is equal to mu into SB. This you will check with this till it converges. We will assume some value, back calculate. Okay, if demand, here you are calculating demand, here this is capacity. Demand and capacity both have to satisfy this value of FD. Okay. You can also develop SD versus T. So if the elastic, you have seen elastic curve was like this, the inelastic curve was like this. So you can read as the elastic directly from here. So this and this are same. Here what I am doing, I am converting SA into SD inelastic. Same is done here. So this star graphically is shown here. Okay. Only thing you have to keep in mind is that here, in case of constant ductility yield spectrum method, the response spectrum, the demand response spectrum is to be read with TE, the initial. Okay. Whereas in case of equivalent linearization method, it was to be read with T equal. That difference is very big.
We have to reduce that when the
We have reduced. Whatever was the ductility, we have reduced. The original curve was this. That was for mu equal to 1. So this is for mu equal to 1. And this is for this mu. We have to, I don't know what I have asked the question, either ductility demand or specific ductility demand means that value of mu you will obtain iteratively at which these two are close. These two match. So that value will give you ductility demand. Ductility demand is nothing but the ductility demand at performance point. And for performance point, this iteratively, this chosen value of SD should be equal to what you are getting from the demand corresponding to the same mechanism or same distributed time. You should still appear to be good. Perplexed. Why? Yes. For SD1, I told you that you can get a good gas from equal displacement principle. And what is this equal displacement principle saying? That you extend this to this and you will get it. Okay. And You have that from here also. If it is in the velocity control rate. This is same. SD elastic and SD inelastic is same. So this curve actually does not depend on mu in this rate. Beyond this point, you can see that beyond this point it does not depend on mu. And if luckily your period comes out to be in this range, okay, you will not require it. But if your period is below this, then you have to use that equation. Okay. Okay. So more you will think, more problems you will try, better understanding you will have. So try to do the same problem by different methods. Then you will understand the difference. Where is the difference? The answer will come out to be different, as I told you earlier. The answer will not be same using both of them. There will be difference in the answer. But the methodology, you can understand. The difference in the methodology you can understand when you try the same question by different methods. Try to solve the same question using different methods. Then you will understand where the difference is. Any other question regarding what we have covered? Yes. Suppose in a question SD versus T, let us say, our design displacement is this much. This is our delta T. And the reduced for him, the reduced SD versus T is this. Okay. Mu xi to R. So for the value of R xi, this comes out to be this. Okay. So here you can see that any period, any value of the period here, it's satisfying this condition. Whatever period you take, the displacement is going to be less than delta T. Okay. So question is which displacement, which period I should take. Okay. Any of these periods you can take. So I told you that the period is governed by other criteria also. So you can take that period which is giving you the maximum energy dissipation. Okay. And at the same time it is giving us the larger size also, so that it can accommodate gravity. So that period can be this corner period. Suppose I select this as my design period, and then I will calculate the SD demand from here. But you have to keep in mind, if you are doing this, the mu will change. It will not be the old mu. The mu is going to change. And when mu is going to change, this curve will also change. And when this curve will change, It may match with the original one, it may not match with the original. Okay. It may be, maybe it is somewhere here. Okay. So then you will get the new value of ST. This iteration you will continue till it converges. The change in mu is small enough so that in successive iteration you get the same value of ST. Sorry? See, T you can take with coordinate period, and when you are taking coordinate period over here, it doesn't matter. Any period larger than this, ST is not going to change.
So instead of that, capacity of my building for delta D is maximum than the demand. Now I will select revise demand, which is maximum of this stock constant demand. Corresponding to that, again I will calculate it. Then again this graph will be corresponding to mu r high.
So in place of this T, which T you are suggesting?
I am not suggesting T, I am suggesting delta D. Delta D.
Delta D. Delta D is given in the question. This is our delta D. So delta D is given.
Delta D is given as per yellow C and all those things. So I need to revise that one because what of the capacity?
How can you revise? Suppose you have decided life safety. In life safety, whatever is the maximum permitted interstory drift, that is constant. That you can't revise. You can design your structure in such a way that it can have any drift below that. So you can choose to have a drift below that, but you can't revise IOLSC. That will remain same. So that we are not going to revise. But any drift, any ST below this is okay. That will satisfy that criteria. So how you should select this? You should select this in such a way that you are getting the maximum energy distribution. You should utilize the maximum energy distribution. Okay. Suppose you choose this value of T, solve it. It will be okay. Okay. But the energy distribution here you will see will be much less and then it will go up. So we are trying to get the maximum energy dissipation which is possible.
And maximum distribution is dependent on ductility. So you are considering
Larger ductility means more energy
More
dissipation.
energy.
So that's why I am taking the maximum displacement in this.
Corner period won't change. Corner period will change.
Corner period will remain same.
So you check according to that period for the generation period.
Okay.
After getting this final displacement, what it means that I cannot design for delta D.
I cannot design for delta D. Okay. So, but I have got now T equivalent corresponding to that. Okay. I have got from T equivalent I can get K equivalent. Okay. And from K equivalent, when I will calculate the force, okay, base shear, so that will be K equivalent. And when I am putting this delta D, in place of delta D, this will be this value of D, not the original delta. So let us say this is delta. So this delta I will put here to get the base shear. And then we will design for this value of V1.
Sir, this delta you are taking is corresponding to the time period you are getting, the time period T to T.
Yes.
You have to take all the delta T, which we have defined previously.
This value of TQ and this value of delta.
Then my force will come less,
Both will come less.
Vy will come less because I am selecting
Vy will come less.
but actual delta T is that one. So K is very equal to delta G, which I was previously said.
So that is a limit. That is not that your structure is to be designed for that. That is the limit. Your structure should not have displacement larger than that. That condition we are satisfied. The delta D we are using here is less than that. What we are designing for. Yeah. So mu, delta, T equivalent, all are related now. 4 seconds or 6 seconds depending on the response spectrum. T equivalent is T under root mu. We can how? But T is not mu. Is T not mu? That's what you are determining, no? T, E, P equivalent mu. These you are trying to obey. T is not mu. T does not mu. Yes. But we do not know the size. All this exercise we are doing to determine size of the cell. We do not know yield strength. We do not know yield displacement. That's why we are doing. Okay. So can you connect now all the points which we have discussed from the beginning of this course? We have to perform a nonlinear analysis. For that nonlinear analysis, we have to estimate hinge properties. For obtaining hinge properties, we need to know the material stress strain curve, material placement, okay, size of the member. Using that, you can develop hinge pattern. From hinge properties, using hinge properties, you can develop a pushover curve. Then you have a demand curve, demand spectrum. Comparing demand spectrum and capacity curve, you can get performance point. That performance point will tell you what performance your structure is going to have, whether it is IO, LS or C. Okay. Now the catch here is that for developing the capacity curve, I need the size and the reinforcement. So to obtain that, we have done DDVD. DDVD will give you the initial size which you should use, initial size and reinforcement. Just size alone is not enough. Size is required even in case of linear analysis. Our conventional design also we need size. But here, in addition to size, we also need reinforcement. So size, for calculating size and reinforcement both, you need some force, Vy or Vb, for which you should design. So you design for that Vy or Vb or Vb, which you are getting from DDV. That will give you the size and reinforcement. So that gives you an initial configuration of the structure, which you can use for performing pushover analysis to develop capacity curve. Once that capacity curve is known, then you can confirm its performance. Okay. Most probably that performance will satisfy your target performance. If it is not satisfied, you have to do addition. Okay. Alternatively, you don't want to use DDVD. You can start with code design, complete the code-based design, estimate its performance using pushover method and performance point estimation. You see whether that is satisfied, your criteria is satisfied or not. If not, revise it. That is another possibility. So somehow you have to have an initial design. DDVD is only to help you in that. Now we have discussed only pushover analysis so far. Pushover analysis is static analysis, but nonlinear. So this is a nonlinear static analysis. In short, we also call NSA or NST. nonlinear static procedure or nonlinear static analysis. We also call it single mode method. We are considering only one mode. And where we have considered this mode? In pushover analysis, where did we consider mode?
Conversion of multi-degree to single degree.
One is conversion from multi-degree to single degree, whereas the initial pushover force when you have applied here, this is also proportional to the fundamental. Okay, so when you are performing pushover analysis, then the lateral load distribution itself is proportional to fundamental mode. So here we have used the mode shape and then converting this into equivalent single degree freedom system, we have used M equivalent, T equivalent. Okay. Here we are using single degree freedom system. Okay. So SA as VD over alpha 1 W and SD as delta 2 divided by gamma 1 phi 1. Both the places I have used mode. So we are using single mode, then we are calling it single mode. Okay. This is the limitation of this, that we are considering only one mode. So in which type of structures such method will be applicable? Where the first mode itself is having significant contribution. So this is applicable to only those structures in which the first mode has significant, that is more than 75% mass participation. For other structures, this is not applicable. In that case, what we have to do? We have to go for nonlinear dynamic procedure. NDP or NDA, nonlinear dynamic analysis or nonlinear dynamic procedure. This is time history analysis. So, if you remember, in linear time history analysis, there were two methods of time history analysis. One was what we call modal time history analysis or modal response history analysis. And what we are doing there, the actual multi-degree freedom system we were analyzing as a series of single degree freedom system. So we were obtaining these responses, and these responses we were multiplying by the corresponding mode shape into modal participation factor, then gamma 2 into second mode, gamma 3 into third, and so on. So this is response, modal response history analysis. In modal response history analysis, we are doing time history analysis only, but we are doing time history analysis of single degree freedom systems corresponding to different modes, and we are adding them. Okay. What advantage we get? Other possibility was that we were solving the equation of motion of the multi-degree freedom system directly. This we call direct response history analysis. And here we are solving the equation of motion directly in matrix form. Single degree freedom system, these quantities are scalar. Okay, here all this will be matrices. Okay, is equal to influence vector. This is something. Where is the nonlinearity? Nonlinearity is this. This component is non-linear. In one of the classes, somebody was talking about hybrid or pseudo-dynamic testing. In pseudo-dynamic testing, what we are doing? This component is coming from test. Whereas here, C and M and UG, these components, these are not changing with time. So these can come from analysis. And we can estimate this quite accurately. But this is because this is unknown. This is changing with X. So this is unknown. This we are getting from experiment. Okay. If we have to do analytical, then Fx also comes from certain predefined rules. That how the load versus displacement curve will be changing with displacement. That too under reversible displacement. Okay. So you have to input what we call backbone curve. This will consist of a backbone curve, which we have discussed. And also the hysteretic model. These two things are needed. Backbone curve to tell how with displacement it will vary, and hysteretic model to tell that under reversal of the loading, how it will follow the Fx versus X part. These two are needed.
In pseudodynamic testing.
No, this is numerical. In pseudodynamic case, this part will this will be replaced by the experiment. So rather than doing this, inputting this numerically, this will come from experiment. So this can come from experiment, this can come from numerical model. If it is coming from numerical model, you need two numerical models, backbone curve numerical model and hysteresis model. In pseudodynamic, this can come experiment. In hybrid, in pseudodynamic, for the whole building it will come. How? You will start with t equal to 0, calculate x, then you go to the next step. Okay. And whatever x displacement you are getting from the previous step, that you will apply here. So you will apply the predefined displacement. Let us call x1i. I is the ith step and 2 is the node. So you will get at ith step, you will apply through actuators, you will apply these displacements, and when you will apply these displacements, you will have to apply force. Some force will be required to apply these displacements. That force you will measure from the load side.
Previous load cycle.
This is previous load cycle only, so not previous load cycle, previous step.
Previous step, sorry.
So at the previous step, the ith step, at which you have got the displacements, you will apply those displacements on your structure. And for applying that much force on your structure, you have to apply some force.
Yes.
That force, F1, F2, F3, that will give you this value. At ith step. And ith step vector you will use to solve this equation at I plus 1 step. Then again you will apply those displacements here and go. This is pseudodynamic. Now you can judge if this is pseudodynamic, what is dynamic? Dynamic test. So three type of tests we are doing: quasi-static, pseudodynamic, and dynamic. What is the difference? This is pseudodynamic, I explained. In pseudodynamics, this equation of motion has three components. This is applied force. So this equation of this is known. Okay. If this and this also you are getting experimentally, then it is dynamic test. How you can get these experimentally? You have to apply x double dot, acceleration, you have to apply velocity. Then only these components will be there. So experimentally you have to apply acceleration, experimentally you have to apply velocity also. That can be done using shake table only. That is possible only if you put your structure on a shake table and subject this shake table to this ground motion. Then NX double dot will also come from experiment, CX dot will also come from experiment, and Fx will also come from experiment. Agree? How they will? No need to measure. Whatever m is here, it will be automatically considered. What you are trying to estimate? You are trying to estimate the displacement. You will measure the displacement. If you are interested in bending moment or rotation, measure rotation. If you are interested in strain, measure strain. But you need not to worry how to calculate m, because you have constructed your structure itself there. So whatever is m of the structure, that is simulated in the experiment. Okay. Similarly, damping. If you have to do numerically, you were worried how to do C. So you have taken Rayleigh damping, that is C is equal to alpha m plus beta k. Or how to get C, that was a big headache. Here you need not to worry. Whatever is damping, that will be automatically taken care of. Okay. Only one problem, and that problem is that you should have a shake table large enough so that you can construct your structure on that, and you should be able to shake it with the given time history. That's the only problem. Otherwise, it is the easiest test where you don't have to do anything. Just construct your structure, shake it, measure. Okay. So first of all, you have to construct the whole structure. Construction itself is costly. Then shake table of that size. You have seen, we boast about our shake table. We have a shake table, but what type of structures we can test there? Can you test a 3-story building or even this 2-story building there? It's not possible. So only 2 facilities in the world I am aware. Maybe in China some more might have come, which we are not aware. But 2 facilities which are very commonly known: E-Defense in Japan and NEES, NEES, NEES in US, where they can test the full scale structures like this. Other shake tables are like this toy shake tables which we are having. Okay. Where you can make a small toy. I am using the word toy because when we talk about our civil engineering structures, then when you make a scaled model of it, okay, the properties change drastically. The properties are very different, and that's why it is very difficult to extrapolate the response which we have obtained from model to the real estate. And we are simulating not only the displacement, we are simulating the non-linear behavior. So plastic rotation, how is it happening, energy dissipation, cyclic degradation. So those things are impossible to model, to simulate on scale. Okay, so that's the big disadvantage, and that's why these small shake tables, you will find very few studies based on shake tables. Shake tables are not being utilized, used. Only those two shake tables, you will find that recent years there are publications. Other shake tables are being used for small, for example, if I want to test false ceiling or some small component, non-structural component, that type of testing can be done. But real structural testing of a building or bridge is not possible here until unless our shake table is very large. So what is the solution? One of the solutions is this, where rather than shaking the whole structure, we make the structure fixed base and apply the displacement. Okay, but when I am doing this, I cannot apply those displacements at the same velocity and same acceleration as the earthquake, or what will be applied in the shake table. That's the limitation. So that's why we call it pseudo dynamic. Okay, I can go on changing depending on the hardware. If I have a very good quality of actuators and hardware, I can apply almost same speed, same velocity and acceleration. Okay, but that is not the purpose. We can reduce the speed because then the cost of the actuators required will reduce. We will not need such large actuators because size of the actuators will depend not only the force which we are applying, and how quickly that force is done, at what frequency it is acting. So earthquake forces, earthquake acceleration and displacement require very high frequency. That type of high frequency will be difficult. Okay. But now there are actuators which are close to it. We can apply almost at the same rate, at which same speed, at which it is occurring really in the earthquake. But we are not shaking. We are applying the displacement here. So mh double dot and ch dot we have to consider numerically. Okay, that's why this is pseudo. Yes.
What is our ultimate aim? Because mx double dot, cx double dot, and fx are getting.
Ultimate aim is to solve this equation, either numerically or experimentally. I am telling you the both methods.
No, displacement we are applying on the structure.
Right.
And the solution from this equation we will get also displacement.
Right.
So what is the aim?
Okay, right. Okay. Aim is because what is happening during earthquake, its mass remains constant. You agree?
Yes.
What about this stiffness?
Stiffness will change.
It will depend on the structure itself.
Yes.
That will come from the test. Okay. So
stiffness will come from our capacity curve. Ratio of this.
अरे कैपेसिटी कर्व निकालने के लिए तो सब कुछ कर रहे हैं. Capacity curve you have obtained numerically, and in numerically you have assumed, you have used some model now. What is model? Model is also an assumption. We have assumed some backbone curve of our hinge, plastic hinge. Okay. We have not used hysteresis at all so far. So, but if we are using backbone curve or hysteresis, that is an assumption. The actual hinge, plastic hinge may not behave in the same manner as we have assumed. So, how to get the actual behavior of a structure? Actual behavior will come from experiment only. Either during actual earthquake, so you instrument the building, and when earthquake will come, you will get the response, and you can record that response. That will be the real response, or you can get from experiment. So the true experiment will be this shake table, but this is very costly. We do not have facilities to do that. So we simplified. How we simplified? The first simplification is this, in which we will do step by step solution of the equation of motion, and the kx or fx we will obtain from experiment. Rest we will obtain from numerical.
Means you are saying that sir, mx is known, ms double dot is known, cx double dot is known. The only problem is with kx. My dot this side is also known. So at each step you will calculate kx.
Each time we will measure kx from the experiment.
Each time corresponding to u double dot g, you will calculate kx. On next step you will use that previous kx, again apply that much force corresponding to that much displacement which we got in last steps. That much
Is it clear now? How the displacement we are calculating from here and then giving it to here, and from here we are going back again to this equation, going to the next step. Okay. So this is our second simplification. But this also, can we test this building even in our pseudodynamic lab? Imagine that I want to test this building. It is a small building, not a large building. I want to perform this experiment even pseudodynamic. Can I do it? So even facilities for this are also not there. So we have to go for further simplification. What is further simplification? That let me identify those members which are crucial, and those I will test. For example, I can consider this beam. Hinges are forming, these beams are identical. So I will take one beam here, whichever is crucial. This beam I will take, and I will develop a test setup in which this beam will be tested with these degrees of freedom. So I have this beam. At the end of this beam, I will have some arrangement, and this arrangement can be controlled by actuators in such a way that it can apply all the 3 degrees of freedom. Okay. Similarly here, with these 3 actuators, now I can apply axial force, I can apply shear force, and I can apply rotation.
So how rotation is applied?
I will, suppose I want to apply a rotation in this direction. I will apply a pull in this side, push in this side. So what will happen if I apply this? This is going to rotate. So rotation will be applied. Actually, you will require 6 degrees of freedom. So you have to connect these actuators in such a way at every end that all the 6 degrees of freedom can be applied. Okay. So what I will do here, even the full structure I am not testing. I am testing only this much. And rest of the structure I will model numerically. And only this fx corresponding to it I will take from the experiment. So I have to do substructuring. There is a substructuring method in advances. I will do substructuring. Rest of the structure will be a numerical substructure, and this element I will get feedback from experiment. Okay, so I can do that testing. Then this will be called hybrid pseudodynamics. We do not have, at least in our nowhere in India. These facilities are also available where we can apply all the 6 degrees of freedom. Okay, this arrangement of the actuators is also not there. So what do? We go for quasi-static. In quasi-static testing, either we test a column or a beam in such a way that when it is bending like this, here the plasticine will form and here the plasticine will form. And we will apply this displacement like this. It is not earthquake displacement. In the previous case, the displacement will follow the earthquake time speed. Whatever displacement is caused by the earthquake, that displacement we were applying. Here, the displacement is just an ideal pattern. Some pattern I will apply. Not the earthquake pattern. And then I can get the hysteretic behavior. Okay, and I will develop my backbone curve and hysteretic. So from here, I will get the backbone curve and these I will use in my numerical solution, which I discussed here. So when I am doing numerical analysis, this is my non-linear time history analysis, where this fx I am using based on quasi-static test of different elements. Okay. Based on that, I will develop numerical. So is it clear?
So
The difference between different type of testing and what we do in numerical analysis is?
So, in case of pseudo testing, we have taken this member from the video. We will perform such tests for each member, and as we develop our capacity curve by making the assemblies, we can do that by making the test for each member and we combine the results of whole meeting.
That's what we are doing here. In this equation, that's what we are doing. We make model. When I said nonlinear model, what does that mean? Each member was replaced by elastic component and member plasticity. So from where that has come? From test only. So you can do test of every member of a building. Again, very cumbersome thing. We do test on similar type of members. Either those tests have been done in past by somebody else, we can take those results, we need not to repeat it because it is a costly thing. Those tests, those components whose behavior is not known to us, those we can take. We can test ourselves. Suppose I am using a new type of column, complete filled column in place of our normal one. For that, the standard or code based backbone curve and hysteretic model are not available. So in that case, what I can do? If the tests are available in literature, sufficient tests are, I can use those. But if, let us say, it is something new which I want to propose, for which the tests are not available, I have to perform my own test. So for that component, I will develop this and use that in my nonlinear time history analysis. Okay. Yes.
Actually, the dynamic behavior is different at the point because the loading rate is different, and you will get the fx value analytically by the consistency number, and how it is driving the dynamic.
See, quasi-static test is different than the dynamic analysis or real earthquake analysis. Not because of the strain rate. Strain rate effects are still small. You can ignore those. Okay. It is more, the difference is more because of the different history of loading. Non-linear behavior depends on history of loading. Linear behavior also depends on history of loading, but when our number of cycles is in millions, then it depends on the history of loading. Normally, if few cycles, it does not depend upon the history of loading. But non-linear behavior depends on history of loading even for few cycles. So, more than the strain rate effect, strain rate effects come into picture generally for strain rates higher than earthquake. The type or the range of the strain rate which are applied during earthquake, the effect of a strain rate is negligible. You can ignore it. Problem is not the strain rate, that actual force is applied at much higher speed and we are applying slowly. That is not a big issue. That will be an issue if we are talking about blast loading or missile impact. There, that problem will be more significant. That is not our main worry. Our main worry is what should be this history? It is not earthquake. If I want to apply real earthquake history, what I have to do? It is different for different earthquakes. First problem is this. It will not be same for each other. Okay. And this hysteretic curve I will get, that will depend on this history. So that's a big problem. That's the major problem, major drawback of quasi-static loading. But this is the best feasible type of test which can commonly be done in our laboratories. So we still depend on it. And we are trying continuously improving it, changing it, standardizing it so that it is closest to the earthquake period. Okay. So this is the main. But whatever it is, based on that, we will develop backward curve and stresses, and then we will solve the equation of motion like this. Okay. Can we use the first method, modal response history analysis, in nonlinear? We can't, because this superposition which we have done here is not valid. So this is not valid or nonlinear structure, and only this is valid. But as I told you earlier also, although theoretically it is not valid, people have tried, and when they have tried it, they call it because it is much faster. Do you agree? It will be faster. We are solving the same equation, but this method of solving equation is faster. Why? Analysis of single degree freedom system is much faster as compared to multi-degree. And we need not to, theoretically, if I want to get the exact result, I have to solve as many single degree freedom systems as the degrees of freedom. We need not to solve all. Okay. We can solve only those which are giving us close to 90-95% contribution. If I solve only those single degree freedom systems, I can get the reasonably accurate answer. Okay. And that will be much easier. But in nonlinear analysis, we can't do that. If we try to do that, that procedure is called fast nonlinear analysis. This fast nonlinear analysis is nothing but modal response history analysis of nonlinear, which is actually not valid, means it will give error. So it gives reasonably good results if the level of inelasticity is less. That means you are designing a structure for, let us say, IO or maybe LS, life safety, so that the nonlinearity is limited. In that case, it will give you reasonably good results. But if you are trying to take it up to collapse, when nonlinearity is significant, this is not giving you reasonable results. Okay, but up to IO, let us say you are designing a hospital, you want to keep it up to IO, it's very good. Or you have nonlinearity in some of the elements, not in all the elements. In some of the elements you have, for example, there is base isolated building, or building with damping devices, where the structure is more or less linear. Nonlinearity is there only in those devices. There also it gives quite reasonable results. Okay, but all these have a problem, and that problem is time history. You need a time history. Okay, so we will stop here, and when we meet on Monday, okay, I will tell you how we can get time. What are the different methods of selecting time? Okay, and that will finish our performance.